So we can play it in full screen.
Oh.
I think it's better
better.
to zoom it up.
I think I will be able to zoom it up because otherwise.
That's true.
Yes.
Perhaps. No, it's not working actually. Can we just?
Yeah.
I was just wondering if you had a piece on the.
We didn't touch it. We don't know where it is.
Okay, no, we can start.
Okay, yes.
Yeah. Great. My name is Bo. I'm a PhD student at UC San Diego. So today I'll be presenting a study on embodiment scaling laws and discuss how we can learn a single policy that can generalize to diverse physical embodiments using robot locomotion as a case study. So generalization has been a grand challenge in robot learning, and scaling laws have been underpinning recent advances in learning policies that can broadly generalize to different environments or tasks. However, generalization along another dimension, physical embodiments of robots, remains a significant challenge. Embodiment level generalization is important because it can bridge the gap caused by many factors: hardware degradation, design improvements, manufacturing differences, or the natural diversity in large-scale cross-source data. So to this, our hypothesis is embodiment scaling laws that training policies on more embodiments lead to better generalization to unseen embodiments. To study this, we create a large embodiment data set, about 1K spanning 1,000 humanoids, quadrupeds, as well as hexapods by varying topology, geometry, as well as joint level kinematic constraints. We then train a single policy that is able to handle diverse observation and action spaces on some subsets of this embodiment data set. And found that the generalization performance on unseen robots improve as the number of training embodiments within each morphology class. If we train these policies on the combined full data set, the generalization performance is even better than the ones trained on individual morphology classes. We also tried simply collecting more data on a fixed set of embodiments and found that pure data scaling is much less effective than embodiment scaling to enable embodiment generalization. So here are some qualitative examples on the training embodiments, as well as on some of the unseen embodiments. So we can see that the data set covers diverse variations across different morphology classes. We deploy the policy trained completely in simulation directly onto the real robot and vary the joint limit of the hardware platform, and the policy is able to generalize to different kinematic constraints as well as different morphology like this one, humanoid H1. So we create diverse embodiment configurations by imposing constraints on the actuators to make them different embodiments on these hardware platforms, and the policy is able to generalize. So overall, this work shows that through embodiment scaling, we can learn a single policy that can operate in both simulation and the real world across many different robots. We hope this study in robot locomotion inspires research progress in other domains, such as manipulation, and contributes to the broader goal of learning broadly generalizable robot policies. Thank you. Welcome to talk to us at the poster session.
Oh, okay. The speaker.
Hello, everyone. My name is Kaiju, and I'm very glad to present our work, Robot Trains Robot here. So during the panel discussion, the professor talked about robot build robot. Yeah, but now I present you the first stage of this thing, which is robot trains robot. So basically our, sorry, should I click or? Oh, click here.
Yeah.
It's possible to maximize as well, the window? Yeah. Oh, cool, much better. Okay, so robot trains robot. Nowadays, we have seen a lot of successful examples of sim to real humanoid learning, which could make humanoid move perform all kinds of locomotion tasks in the real world. However, there is yet a real-world humanoid reinforcement learning project. And in this work, we got inspiration from how human parents will like hand their child into working. Present our hardware and algorithm system where a humanoid a robot arm teacher tries to teach a robot humanoid learner. And we could look at this video show. Oh no, I should have put all the, well, anyway, so this is basically, so you can have some imagination of this robot arm, which it could move freely in the XY plane in compliance to follow the robot moving while moving in the Z direction to form a curriculum. So when the robot works better and better, the robot arm will gradually push itself down and the robot will like get less help from the arm. So besides that, this system could also provide like automatic reset and provide some informative reward signals that is hard to require in the real world. So apart from the hardware system, we also, yeah, this is part of the system. And like we have a robot arm, we have a pulse torque sensor, we have a programmable treadmill, and we have this little robot. And it's periodically updated by the workstation, which is running PPO. And besides the hardware innovation, we also have some new algorithms. So basically, our project gets inspiration from RMA, which estimates the real-world dynamics from a data. So in the first phase of our algorithm, we will basically train some dynamics condition policy given the domain randomization parameters, and we will fit it into the policy by a few other modulation layers. And in the second stage of this policy, we will train one single and uniform latent that could let the robot work in different domain randomization environments. Once we get this latent, we could use it in the real world to roll out the policy and let it perform real world learning with the help of our hardware system. And the whole training is very stable and very sample efficient. So in this figure, we could see that if we fix our robot arm and let it only be at like fixed level, whether it is the higher level or it is the lower level, it will eventually get much less behavior performance when evaluating at the final position compared to our approach. And also the dynamics latent fine-tuning could have very good sample efficiency compared to directly optimize the policy in the real world using TPO. So we could say the TPO curve will diverge. Okay, so besides, yeah, I think I have the, besides the fine-tuning task, we also perform real-world learning from scratch. So in this task, the robot can learn to swing itself up under the robot arm. And this is real-world RL, and the robot arm could help the robot to like cancel or amplitude its movement during the procedure. And all of this is done like in less than 20 minutes. Yes, by the way, this robot is like a own designed humanoid robot by Stanford University, Houchin and Kenmont. It's called Tolerbot. Okay, cool. So I think that's it. And finally, there is, oh yeah, I think that's our presentation. Welcome.
Hello, my name is Hao Huang. So today I will be talking about our paper, Touching the Wild, Learning Fine-Grained Manipulation with a Portable Visuo-Tactile Gripper. So this work is collab with Xingyue Zhu and Professor Yunzhu Li. So using Yumi gripper, the operator can feel the contact between the object and the robot fingers and naturally adjust their motion to help better complete the task. So however, such haptic dynamics are not captured by the data set. So that's why we add tactile sensor on the gripper. But in the wild, Visuo-Tactile data is not easy. So for this paper, we mainly do two things. The first thing is that how we collect data and visual-tactile data in the wild. And the second thing is how we make use of this kind of large-scale visual-tactile data. So here is our visual-tactile data collection system. We design a lightweight, low-cost gripper with piezo-resistive tactile sensors. It's easy to carry outside to the lab, and this enables large-scale visual-tactile data collection possible. So this is how we collect data in the wild. And we could simply bring it to the outside and plug the cables to the laptop or any Ubuntu device, and we can easily collect data. So we collect large-scale visual-tactile data and from 2007 episodes across 43 different tasks. So after we got the visual-tactile data set, what we will do next? So we first we pre-train a visual-tactile encoder using cross-attention reconstruction. And after we got this encoder, it's in this red area. We will use this encoder for the downstream imitation learning. We find that this encoder could help us to build the correlation between RGB image and the tactile. And this could help us to train a robust policy. Okay, let's see some demos. So this is Professor Yundu's favorite demo. We reorient the transparent tube and the human will interrupt it and interrupt again. And the robot will continue to reorient and then do an accurate insertion. Let's see more comparisons. This is, we want robot to get some water from one container to another. And this requires very detailed force control. And this is a baseline policy. We find that the baseline policy, even though we put tactile here, but here we didn't use the tactile. And we find that the policy will just skip to expel the water. Yeah, because for the vision only policy, it didn't know the actions. Okay, yeah, please come to our poster and hardware demo. I bring the tactile sensor here. If you want to have a try, you can come to here later. Okay. Thank you.
Hi guys, I'll be introducing some of our preliminary results titled Efficient End-effector Co-Design by Demonstration for Deformable Fragile Object Manipulation. Our motivation lies in first, co-design is not very well explored for this particular problem. Sometimes people focus on hardware design, some people focus on control problem, but we want to optimize both simultaneously, kind of. And we think this is useful because you can imagine human hand configuration as the hardware design and the grasp pose as the control. By having a poor combination, like ones on the left, you cannot pick up the tofu very efficiently. But with better alternatives, you can pick them up quite robustly. So formally, our objective is to optimize for end-effector finger geometry, as well as to find a proper control for that hardware. And our goal is to minimize the internal stress applied to the object while maintaining a good task success rate. And as in our title, we focus on efficiency a lot. And the reason is accurate deformable body simulation is quite costly because we, in addition to deformation state, we also want the stress information, which requires a fine-grained simulation to get that. And empirically, our machine runs 0.3 seconds per environmental step that is measured in real world. And if you run something like PPO, you would probably need at least 40 hours just to collect the samples. So to promote efficiency, we used this two-stage Markov decision process studied in previous works a lot. We use this because it's quite efficient. We have two stages in the MDP. First is the design phase, where the action controls how the finger design looks like. So AD will control how the finger looks like. And in the control phase, it's quite straightforward. The action just dictates how do we move the end effector. And our framework consists of first collect some demonstration to further improve the sample efficiency. And we learn a co-design policy on this dual MDP, which learns both the design action and the control action online. And finally, with the converged co-design policy, we fix the best design and fine-tune the control policy to best maximize performance. And here we address two questions. First, how do we parameterize the design space? Because we're dealing with deformable objects, we want some design space that preserve curvatures, right, to better conform to the objects. And the second question is, how do we collect design demonstration? Because control demonstration is quite easy to collect, you just tell it up. But design demonstrations, how do we get that? So to address the first question, we use, sorry, I'll speed up. We use something used before, like it's cage-based deformation. It's basically deforming a mesh by controlling a cage. But in addition to previous works, we discovered that this promotes a wide range of shape generation. Like we can generate a shovel out of a sphere by only having 7 handles. Sorry, it's 15 handles. And the second is a human can generate designs in CAD softwares, but we don't know what parameters correspond to those shapes. For that, we leverage the fact that the cage-based deformation is differentiable, so we can propagate to get the, the parameter. And this also shows the flexibility of the design space. You can generate a lot of shapes just from a sphere. Okay, I will just skip over these. It just says the framework works, and we deploy it in real, and it works. Finally, some insights maybe in how to improve the efficiency for your co-design problem. First, you can always adopt two-stage MDP for its empirical efficiency. And though I haven't mentioned, but we used RLPD and a sample efficient RL method with demonstration to improve sample efficiency. And lastly, cage-based deformation offers a parameter efficient yet flexible design space. So you may consider these. Sorry for the overtime.
Oh yeah. Oh, God. Sorry, we'll play the video.
Morphology-aware learning can enable zero-shot generalization to novel morphologies, as shown in prior works. However, current evaluation setups often have limited variations in the robot set, have data contamination, or focus on some specific tasks. That is, they do not adequately support the study of cross-embodiment generalization in manipulation. We introduce Anybody, a benchmark suit designed for cross-embodiment manipulation. First, it dispenses a diverse set of robots with simple to complex link structures, covering both artificial and real-world morphologies. Second, it supports evaluation across tasks of reach and push and scenes with and without obstacles, and state-based and point cloud-based inputs. Further, it enables systematic study along 3 axes of morphological variations. Interpolation, robots share a common structure. Composition, test robots are composed of trained robot parts. And extrapolation, robots with different link structures. Each category includes tasks of varying difficulty. We evaluate both single embodiment SE and morphology-aware multi-embodiment ME agents trained with reinforcement learning. From our experiments, we find that ME agents can achieve faster conversions given the same number of interactions. Second, zero-shot generalization is mostly limited to the interpolation regime. Further, fine-tuning ME agents for complex scenarios may still underperform SE agents even with 30K environment steps. Finally, we find that small design choices in architecture and training can significantly impact performance. In summary, any body is a benchmark for studying cross-embodiment generalization in manipulation, featuring diverse morphologies and structured evaluations. Currently, it only includes reach and push tasks, which we plan to extend in future work. Thank you.
Thank you.
Morphology aware.
Hi, everybody. I'm James Clinton. I'm a first-year PhD student at UC Santa Barbara, and today I'm going to be presenting our preliminary work on learning to extend legs of a transformable wheel robot. So when we look at wheel-based systems, there are two primary options, wheels and WEGs, each with their own advantages and disadvantages. Wheels are really great for flat terrain as they're super efficient on that and can get over it very smoothly, but they often struggle on rough terrain and larger obstacles. Whereas WEGed robots are less efficient on smooth terrain due to the bumpy nature of their movements due to the WEGs, but they're better able to climb over rougher terrain. So one way to combine both of the advantages of both these systems is through transformable wheels. Transformable wheels shift between wheeled and legged wheel modes in order to combine the advantages of both systems because they're able to shift between the two methods of locomotion. They're stable and efficient like wheels on smooth surfaces, and they're versatile and capable like WEGs on rougher surfaces. So we've decided to explore a transformable wheel robot, and we wanted to look into what kind of controller might be a good fit for a transformable wheel. So transformable wheel robots are inherently stable due to their four wheels, and they have helpful proprioceptive measurements due to the measurement of tilt and speed that we can get from an IMU. And they also have very continuous transformable states. And in our design, we have a coaxial geared shaft that allows us to continuously shift between the wheeled and legged wheel modes. This made it a good fit, as we saw, for proprioceptive reinforcement learning. So we wanted to pursue blind locomotion RL. Using our simulation environment in ManiScale 3, we have an environment set up with a simple step obstacle and a model of our robot. We use PPO for training our RL. We use IMU and encoder inputs, so we are fully proprioceptive. And we came up with a reward that penalizes velocity error and minimizes leg extension time to improve the efficiency of our robot. So we have some preliminary experiments in which we've conducted tests in flat plane environments and step obstacle environments. We found that it was able to learn to climb over. And we also have a simulated demonstration where first the robot approaches a step with the legs starting retracted. As it climbs over the step, it extends the legs outwards. And then once it climbs over, it is able to retract the legs in order to maintain efficiency over the smooth terrain. In the future, we're hoping to continue exploring the design of the mechanism, potentially through co-design. Look into more complex training environments beyond the single step obstacle, and continue working on further policy development. In particular, one of the things we're hoping to do is sim-to-real experiments on continuous terrain. As you see here, we have a simulated continuous environment, as well as a similar environment 3D printed in the real world. Yeah, thank you for listening, and I hope to talk to you all at the poster.
Hello, everyone. My name is Tianyu. I'm from UPenn. Today, on behalf of my authors list, I'm going to present VLMgineer, Vision Language Models as Robotic Toolsmiths. So in this project, we're trying to answer a question: can today zero-shot VLMs help robots autonomously design their own tools and figure out how to use them? So in short, can we use VLM to do two design and action together? So let me show you a simple example here. So here is a plate on the table, and we're trying to see if the VLM can come up with a tool to make the action simple. And VLMgineer is designed for that. And here's the design that the VLM come up with a lift fork that goes under the rim of the plate and then lift it up. And then we have many more examples that we can talk more during the posters. And you can see like there are a lot, although there are same tasks, but there are a lot of variety of different designs from the VLM. And how we do that, I'm going to introduce the method. So first we give it environment code from PyBullet and also a task description saying what kind of problem the robot encounters, as well as system instruction on what kind of output we want. Then the prompt will be given to the VLM agent, which will then output samples of URDFs as code and also the action trajectories. The action consists of End-effector position, orientation, as well as gripper opening. And then we evaluate all of the samples in simulation to pick the top K candidates. And then we use the candidate to do evolution, also using VLM. VLM will decide what to mutate and what to cross over in the URDF and the actions. And then we just keep looping over this loop, and we will get the final optimal design after that. So during this project, we find it hard to find a benchmark in simulation to test, to evaluate all the designs and actions. So because a lot of the benchmark and simulation tasks are designed for a robot with a normal gripper. So we come up with 12 tasks that's beyond usual robot capabilities with two-finger grippers. Some tasks that are interesting, including the one here that there is a cube inside a tube, and you need to design a tool basically to try to get the cube out. And our method generates a long bar with a thing at the end to insert into the tube and then poke it out. And we can show more video during the poster. So we compare VLMgineer with two different baselines. One is just the original finger gripper, and also we invite 3 human subjects to do human-specified prompting for the VLM. So the 3 human subjects, including a LLM experts and also robotics experts, and also a person from outside of technical field. And our method achieves the highest for all the task average we just showed. And please come talk to us at the poster, and please enjoy all the tools and action we have. Thank you.
Oh, okay. Yeah. Here. Yes. Yeah, the next slide.
Oh. Okay. Okay. There's no mic or anything. Oh, I'll just speak loud. Yeah. Hi, my name is Tony, and I'm here to present DexWild, Dexterous Human Interactions for in-the-wild robot policies. So we all know that data is really important, but where should we get the data to train our robots? One way is to use in-the-lab robot teleop, which gives us really high-quality data, but it's extremely hard to get the diversity that we need. The other way is to use human videos, which is high in diversity, but it's really hard to use in training. So what if we want both quality and diversity? Well, we could just take robots out of the lab, but robot teleop in the wild is extremely hard. That's why we're introducing DexWild, a human hand data collection system for collecting high-quality, diverse demonstrations in the wild. There's 2 parts of DexWild. a DexWild system, which is a human hand data collection system, and a co-training pipeline that combines human and robot data for robust policy generalization. It's extremely easy to bring DexWild to all different places and collect demonstrations. In total, we collect almost 10,000 demonstrations in 93 unique environments. And we really tried to cover all the distribution where the robot could be. And we brought DexWild everywhere. Even though DexWild is extremely portable, we make no sacrifices in fidelity. We use mocap gloves for precise hand pose estimation. Then we capture high quality task-centric observations using wrist cameras. And lastly, we use Aruco markers to track the wrist pose, which is really robust. Sorry. Can I go back? Oh, what the hell? Sorry. Which is extremely robust compared to other methods like SLAM. And to ensure our data is robot agnostic, we mirror the camera setup on the robots. This allows us to align the observation spaces. As you can see, the human and robot data looks extremely similar. Then our human hands can be retargeted to any robot hand, even ones that don't exist today. This means that DexWild data can continue to be used as hardware improves. So once we collect the data, how do we use it? We choose to combine the data and co-train human and robot data together. And we do this by sampling using a 1:2 ratio as we found during our ablation studies. And you can use either ACT or diffusion policy. We test our policies over 5 tasks in 53 environments, and we find that our policies generalize 3.8 times better than training with robot data only. We also find that our policies work for more complex bimanual tasks that require coordination between both arms. For generalizing to new robot arms, we're able to zero shot directly. And for generalization to new hands, just collect a few demos of the new hand you have in the lab and co-train it with the human data that you already have. If you find our work interesting, please check our website. And there's also a lot of great work, such as DexUmi, which is also in the similar direction. So I encourage you to check out their work too.
Thank you, Tommy.